Joe's. Great, cool. Yeah, so oh, do you want to click on the screen there, Joe? I don't know if my clicker is working. Okay, there we go. Is that working? I think it's sharing from over there. So that's the yeah. Presentations over there. Oh, that working? It might be the screen recording. I can try and reshare. Yeah, why don't you do that? We won't spend too much time on it, but if it works, it works. Is that you or me? Okay. All right. We're getting there. Okay, so robot structured environments, that was well understood and it works. However, as we move robots into unstructured environments, should I stand over here? As we move robots into unstructured environments, like these two robots from DeepMind playing soccer here, it becomes more and more useful and more necessary actually to use learning-based strategies to figure out how these robots should behave. So in this example here, these two soccer-playing robots, in part in simulation and in part in the real world, are going to play hundreds of or thousands of games of soccer against each other and use that data to develop better skills and to learn how to behave. And importantly, when systems that use learning during deployment, so not only in the development process, say when you gather a bunch of data with your robot and sort of develop the behaviors there, but also during deployment, we create systems that are highly adaptable and highly robust. So one excellent example from UC Berkeley down here in the lower left is a robot dog that has never been on this trail before. It's never seen this kind of terrain before. But as it wanders down this trail and slips on the uneven and loose terrain and on these routes, it's using that data to adapt its locomotion strategy to better walk on this trail. So I guess I got to be over here. So, okay. So that, well, okay. So that leads into the core motivation of my work, which is all of these learning systems depend on being able to gather a lot of data. So that's kind of a bottleneck in a sense, right? Because if we have one robot working alone, it can only gather so much data at one time. However, teams of robots, because there are more sensors available and they're all independently experiencing different things about the environment, are able to multiplicatively gather more data faster than a single robot. So in this example from Zhejiang University in China, you see 10 drones flying through a forest, and we're getting 10 times the images, 10 times the data about this forest. And so based on that data, we can do faster learning more efficiently and more performantly. But this introduces a new challenge, and that challenge is, okay, we have all this data from all of these different robots. How do we actually learn from that data? How do we do that efficiently and effectively? And that is the core idea behind the work and the core challenge that the work that I did during my PhD seeks to solve. So in this defense, I'm going to talk about 3 separate projects that I work on. Each is an algorithmic contribution towards collaborative multi-robot learning. The first one is distributed multi-target tracking. In this work, we're going to talk about how a fleet of autonomous vehicles can work together to collaboratively track a bunch of targets in a scene. In the second work, I'm going to talk about a general purpose algorithm for distributed neural network optimization. And we're going to show that using our algorithm, teams of robots that gather data together can collaboratively learn neural networks. And this is super useful for a bunch of broad range of tasks in multi-robot systems. And then finally, my last work that I'm going to talk about is possibly my most applied work. And that's going to cover how we can use data from a team of robots, again, to gather a bunch of information about the geometry and the contents of a scene and use that data to create extremely high fidelity maps in real time. And this is going to use a technique called Gaussian splatting, which I'll be discussing later. Scared to hit this too many times. Yeah, we could swap it out. See if that works. By the way, a lot of this talk is going to talk about wireless communication. So you can say it always works, it never fails. Okay, so distributed multi-target tracking, how does that work? Before I can really talk about any of these collaboration things, and I'm going to talk about the distributed multi-target tracking, I just want to briefly discuss a little bit of vocabulary surrounding robot communication. And so within robotic systems and systems of multiple robots, communication is essentially the thing that enables collaboration, right? Before anything can happen, before any two robots can work together, they need to be able to communicate. So this is a central idea. And within multi-robot systems, there's two main paradigms, main models of communication that we use. One is centralized communication, where all of the robots communicate with some existing infrastructure, some central control node. And then there's a distributed paradigm, which is a little bit more exotic. Centralized communication infrastructure is typically what we think of when we think of wireless communication. That's Wi-Fi, that's cellular data, 5G, all those things. Distributed networks are a little bit more exotic, but they're actually becoming quite a bit more common now that recent advances in hardware and radio transmitters have come out. And in distributed networks, rather than communicating with some central control node, the robots communicate with each other directly. So they're doing direct peer-to-peer message passing. And this has some benefits in terms of robustness and other things. Okay, so talking about multi-target tracking, what is our problem setup? What are we trying to exactly do? We start by looking here at sort of the basic setup for this problem, and we have a bunch of vehicles that are doing some tracking in green, and they're connected in some network that is a distributed network, as I mentioned before. And each of these vehicles that is doing the tracking gets some measurements of some target vehicles. So that's going to be these vehicles in red and in blue here. And you can see indicated by these lines the measurements that they're making. So as they make those measurements, what we're going to do is use this communication infrastructure that we have between the different tracking robots to collaboratively estimate the position of these target vehicles. And we're going to do so by estimating not only their current position, but also a rolling window trajectory of where that vehicle has been. And I think this problem is super important for specifically for in the case of autonomous vehicles, because by connecting and communicating with each other, this system as a whole is able to develop a larger scale awareness of the scene than any individual robot working alone. So an excellent example, and one that really motivated this work, is that in this case, this vehicle down here is not able to observe the red vehicle, but by being connected to the rest of the vehicles in the network, it still gets information about where this red vehicle is. So in a different sort of setup, perhaps if this bottom vehicle is coming around a corner and it hasn't seen this red vehicle that's possibly making an illegal right turn, it can still know that it's there and know to stop before it gets to this corner to avoid a blind corner collision with that red vehicle. So we're trying to develop this city scale awareness in this autonomous vehicle fleet. The general sort of framework for this problem, or the general classification of this problem, is multi-robot estimation. And within the within the multi-robot systems research community, there's lots of different approaches that try to tackle this problem. Sort of the main competitor that we had when we started working on this work was called the consensus Kalman filter. And that uses a fairly complex system of sending and receiving measurements and covariances between different robots to continuously update some local filters that each robot has. Some other ones are all-to-all measurement communication, essentially where you blast your measurements out into the network. So all of the different robots are flooding the network with their measurements, and then also receiving all the measurements from all the different robots. That is inherently kind of bandwidth intensive and not necessarily very efficient. And then finally, some partitioning approaches that are a slightly more complicated way of breaking down the problem that ends up not really recovering very good solutions. So this is like three vastly different ways to solve this problem. I'm going to introduce a fourth that I would argue is a little bit better and a little bit more structured. And that's going to take advantage of a paradigm or an optimization formulation called distributed optimization. And so I'm going to first start by discussing what distributed optimization is, and then I'm going to show how it can be applied to this multi-target tracking problem. So the basic setup for distributed optimization is this. Very generically, we have some system of networked robots using a distributed communication network. And each robot has an independent objective function. This is called the local objective function of that robot. And so usually these local objective functions are defined by some kind of data that that robot has gathered. And in our multi-target tracking case, it's going to be those measurements that we make of the different target robots. And if you see down here in this made-up case, we have these functions being a bunch of quadratics. And what we're trying to do is not necessarily optimize the independent objectives here, but we're trying to optimize the sum of these objectives. So this basically says, rather than any one robot doing the best it can, we want to do the best for the entire team of robots. And if we formalize this in an optimization problem, so we write down the minimization, you can see here that we're minimizing over some sum of these local objective functions. And then to make our lives easier later, we're going to introduce some auxiliary variables here, x1 through x4. And you can think of these as local variables that each independent robot keeps track of. But since each one is a local variable, we need to add a constraint, which we call the consensus constraint here, that says at the end of optimization, all of these local variables should agree. So that means that at the end of all of whatever we're doing with distributed optimization, all of the robots will have the same answer. So it's like solving the main problem without actually, Okay, so that's the basic formulation for a distributed optimization problem, and it's very general. These objectives could be anything, and you could also add other constraints here if you wanted to. Once you've written down a distributed optimization problem, once you've translated whatever your multi-robot application is into a distributed optimization problem, you can actually then directly take this formulation here and use any number of existing algorithms. So actually, this original formulation for the distributed optimization problem was proposed I think in the early 80s, maybe even the 70s. So there's like 50 years of research in distributed optimization for mathematically and algorithmically how to solve these problems. Probably hundreds or even thousands of papers have discussed different ways of doing it, and different methods work well for different conditions of this problem. In fact, this is so useful for multi-robot systems that for like 3 years, we worked on a survey that discussed how to apply different algorithms from distributed optimization to different multi-robot problems. So not just this distributed tracking problem. But how do these algorithms actually work kind of at a high level? And I think this is useful because it helps us understand not only the general problem of distributed optimization, but I think it'll serve to clarify a little bit of the later work that we do that I discuss in this presentation. So we start obviously with our system of connected robots here. And then the generic distributed optimization algorithm has just a few steps. And a lot of these are common between all of the different methods. Even though there are thousands of different methods, they all kind of fall into slight deviations of these basic steps. So to go through the general form of this, we start with our robot. And let's look at it from the perspective of a single robot, because I think that is a little bit more straightforward to understand. So this one robot has its local objective function, as I mentioned before, and then some data that it's gathered that sort of informs this local objective function. And the first thing that we're going to do to start distributed optimization is take an initial guess at whatever that x1, that local decision variable that this robot is going to maintain is. Once we've made that initial guess, what we're going to do is enter into a process that repeats a bunch of times over and over. And that process has 3 steps. It begins with communication, where we take whatever our decision variable is, that local decision variable, and we send it out to our neighbors in the communication graph. As we're doing this, simultaneously, we're going to receive some decision variables from our neighbors, right? So x2 and x3 come from other robots. Once we've received those values from those other robots, what we're going to do is we're going to take those values and we're going to use our local data as well as those values to update our local decision variable. And the form of this update, which I've tried to write as generically as possible here, is usually some kind of interior minimization, so like a secondary level of optimization that uses our local objective function along with a term that encourages consensus or encourages agreement between all of the different robots. And importantly, this line exactly here is usually where 99% of distributed optimization techniques make their contribution. So variations on how to solve this problem are exactly what each distributed optimization algorithm does. So we solve this local update, and then we update our decision variable. So now x1 has become purple because it's changed value. And by carefully performing that local computation and repeating this process of communication and computation over and over again, we eventually converge to a solution. And we know we've converged to a solution when we check for convergence by seeing if all of our neighbors are sending us the same value. So if we receive essentially the same value from our neighbors, then we know that they've converged to a value and that also we've converged to a value. So we have satisfied that consensus constraint that I showed in that optimization problem before. Okay, so that's the basics of how distributed optimization works. Now, so let's apply it to our target tracking problem. To set it up, the main thing that we have to establish is what that local objective function is. So the way we're going to tackle this tracking problem is through a rolling window maximum a posteriori optimization. And that essentially means that we're going to form some objective that's based on our estimate or based on some modeling assumptions. And then we're going to optimize that objective to then produce our estimate. And so this is our local objective function, which looks kind of complicated, but I'll break it down really quickly here. So the first term in this local objective is related to the dynamics of, or some model of the dynamics of the vehicle that we're tracking. So this says that we just update with some linear dynamics and some Gaussian noise. Now, this doesn't necessarily apply to the types of vehicles that we're looking to track, but it's a fairly consistent modeling assumption. It tends to be pretty robust in practice. This is basically the same assumption that Kalman filters make. Secondarily, in the second term here, we have our linear measurement model. Again, similar to Kalman filtering, we make these linear assumptions. And then the third term is our rolling window term. This essentially says this estimate for the new position of X here, or the new position of this target robot here, should be consistent with this trailing trajectory that we've had before. So it sort of serves to inform this new position, but also this new measurement then can update this tail here. And it's rolling because at every time step, we drop the oldest part of the estimate of this trajectory and we add a new one. So you can imagine that as this car drives, this tail sort of follows it, and that's the tail of estimates. Great. So this is a little bit restrictive, these linear assumptions, but actually in practice, we can show that we can do this with nonlinear components here, but it changes a little bit of our analysis, and we didn't necessarily do that in this work. Okay. Cool, so now we can tackle our joint problem. And by that, I just mean the full distributed optimization problem. So you can see here, our form is consistent with that basic form of distributed optimization problems that we had before, where we have the same objective from the last slide, but summed over all of the different robots that are tracking any particular vehicle. And then we add this consistency constraint or this consensus constraint down here to be sure that at the end of optimization, all of the robots converge to the same value. The algorithm that we chose to use for this work for distributed optimization is called consensus ADMM, and it's based on the alternating direction method of multipliers. And this is an augmented Lagrange. I'm not going to get too much into the math here, but it's an augmented Lagrangian-based method. So we have a dual variable that requires a linear update. This is during the local computation. And then we have this primal variable update, which is our xi's that we're interested in updating. And this looks like a sum here of a linear term, a quadratic term, and then our local objective. And if you remember, our local objective from the last slide is just an unconstrained quadratic program. So this whole thing here, even though it is an interior maximization, is actually just matrix factorization and inverse that we need to perform to do that local update. So it's extremely quick. And this is sort of similar to ideas from Kalman filtering, where you're applying some kind of matrix inverse to update your values here. So there's some parallels to filtering, although it's not exactly consistent with that. And because these local objective functions are all convex, we can actually take some guarantees from consensus ADMM and say that we're guaranteed to converge to the minimum of the global problem. So we're guaranteed to find the global optima of this optimization up here if we use these local update functions. And then finally, yeah, again, this is closed form down here. So even though we're performing this distributed optimization every time we receive a new measurement, we can do it extremely quickly in the matter of, like, say, a couple of milliseconds. So it's not too much of a concern that we need to do it repeatedly. Great. So what does this look like in practice? Because that's all very mathematical, very theoretical. We decided to test our framework in simulation rather than sending 150 cars out on the road, because that might be a little impractical for our paper. But we wanted to keep it as realistic as possible. So we use all of the same tools that you would use to track vehicles on an actual autonomous car. So we use segmentation images from the simulator and depth images from the simulator to estimate bounding boxes and then make measurements. So even though we are observing the sort of we are still making the linear measurement update assumption, our measurement model is actually not strictly linear. So there is that modeling gap there. But we show that basically it still works just fine. And then on the right-hand side here, you can just see a brief example of some cars driving around, and they're connected, making some measurements of a target vehicle, which probably we'll miss. OK, so a bird's eye view of this working on, say, like a 4 or 5 block area is shown here. And you can see there, I think there are like 100 tracking vehicles. I mean, they're all driving around and tracking some other vehicles in red here. And so if we zoom in on one particular target vehicle, we can see here it's trailing its rolling window estimate. And each of the vehicles that's highlighted in green here is actively making measurements of this target vehicle. And maybe you can see it over in the corner here. This is like sort of the live rendering of the carless simulation for what's happening on this side. So quantitatively comparing our method to the consensus Kalman filter, which is kind of the existing state of the art at this time, we can see that our solution is orders of magnitude actually more accurate to the true underlying value of the trajectory than that consensus Kalman filter. And that's mainly because even though Kalman filtering is an optimal process, the consensus Kalman filter itself has to make some approximations that make it not necessarily converge to the optimal value. So it has some steady state error. On the right-hand side here, this I think is like a little bit of a weird graph, but I think it's really interesting to consider. And this is the accuracy of the tracking if all of the robots didn't collaborate, and that's what's in red. So this is on the top here. This is each individual vehicle working by itself. And then the blue lines down here are the accuracy of the tracking over time of all of the vehicles working together. And you can think of this as two regimes, right? This is what we currently do in autonomous driving, right? There is no communication between vehicles. There is no collaboration. And so we get less accurate estimates. But down here is what we could be doing if we had collaboration between vehicles, if we did have communication. You can see there's a several orders of magnitude benefit in the accuracy of tracking of vehicles if we just use a little bit of communication. Great. So that was multi-target tracking. Now I'm going to talk about distributed neural network optimization, and you'll see some parallels in the formulation of the problems that I talk about here. But this is more of a contribution on the algorithmic side, on the development of a method for actually being able to do distributed optimization on this specific kind of problem, and not necessarily like the last project, which was more centered around providing a formulation for solving the target tracking problem. Great. So distributed neural network optimization, it's the name of the problem and also the name of the algorithm which we propose for solving the problem. So it's a bit of a chicken and egg thing, but it's just what we named it. So I get to decide, I guess. The basic setup is very, very familiar. We have a bunch of generic robots in this case, not necessarily autonomous vehicles. And they're maybe driving around somewhere or doing something, and they're each independently gathering some data. So they each have this local data that they've developed. And what we're going to do is try to train neural networks on all of that data. So you can imagine each of these individual pieces or chunks of data that these robots have. If we took them all and put them on a server and trained a neural network, we would get some optimized model. But what we'd like to do instead is not do that data aggregation and instead use distributed optimization to optimize these neural networks. And this data could be anything. It could be LiDAR scans. It could be, I showed that example of a robot slipping earlier on a trail. It could be interactions with the environment. It could also be interactions with people, say personal data or something like that. Okay. In terms of related work, again, within the field of distributed optimization, there's been like 50 years of time for people to propose methods that work for non-convex scenarios. So neural network optimization is just a non-convex optimization problem. But the issue is that even though these methods can theoretically solve these problems, practically they use some mechanisms that actually are very hard to make work with the specific sort of setup of neural network optimization. And that's kind of what our work is interested in solving. So these methods, while theoretically they do work, don't in practice actually work that well. Oh, whoops. Great. So to set up our algorithm, we're going to tee up the same exact kind of distributed optimization problem. And here we have, again, our sum of individual objectives and then a consensus constraint. And again, reminder that these individual objectives are quantified or qualified by some data that makes them individual to the particular robot. And then again, we're going to start here with consensus ADMM, but we're going to make some adaptations to our formulation that are going to help us solve distributed optimization problems on neural networks specifically. So we have our same linear dual update. And then our primal objective here, unlike the last project that we talked about, is no longer some quadratic thing that we can find a closed form solution for. Instead, it's actually kind of a mini neural network training problem on an individual objective of each robot. So if we exactly optimize these, we're going to waste a lot of time. And actually, the main idea behind our work and what we show in some results is that you don't have to exactly optimize this. Instead, what you should do is use your traditional tools in neural network optimization, like ADAMS, like RMS-prop, and approximately optimize these interior or these primal local updates. And by doing so, you actually end up with an algorithm that still has some of the guarantees that are really nice about consensus ADMM, but doesn't waste a bunch of time solving these to high accuracy. And so the result is, even though this problem is non-convex, we can still guarantee that all of our robots are going to reach consensus. So they'll at least agree at the end on the quality of, or on the neural network, and also that we converge to a local minima of the of the global problem. Great. So some examples now to show that it actually works. This is a bit of a toy problem, but I think it's really interesting to consider some of the main benefits of using Dino. So the MNIST problem, if anyone's unfamiliar with it, is a digit classification problem where you have pictures of handwritten digits and you'd like to figure out what the value of that digit is, so 0 through 9. And in this problem formulation, we really wanted to highlight the fact that you don't need all of the data on any one of the robots. So in our setup, we only provide each robot with examples of one single data type. So one robot will have all zeros in its data set and only examples of zero. But if they work together using Dino, you can see on the left-hand side here, as I'm visualizing the evaluation data set, they converge to a solution that's able to classify all of the different digits. So this shows that through collaboration, these individual robots, which would only be able to get 10% accuracy on the joint evaluation set, are able to get nearly 99% or 100% accuracy. And what's interesting also is you can see that at convergence here, the different models agree or sort of get the same thing wrong, right? So you can see that they all sort of miss these three examples here. And that shows that not only do we get to a good solution, but that all of the different robots kind of agree in the space of neural networks, which is good. Great. The second example, which is a little bit more robotics oriented, is focused on 2D neural mapping. So very quickly to explain what that means, we have some robots that are getting LiDAR scans of a 2D environment. In this case, I think it's the floor plan of some building in Denmark or something. So they're driving around getting these scans. And what we're going to do is use that data to train a neural network that says, given an XY position, what is the density of that position? And so that means like walls are going to have high density and open floor plan areas are going to have low density. And you can see here the result of each robot only using its local data. It's able to recover sort of the shapes of the rooms that it's been in, but not anywhere else on the map. And that makes sense because it doesn't have data in those places. If we use Dino again, we can see, as expected, we achieve a global result for the map that is accurate and agreed upon by all of the different robots. And you can see here the communication graph that they have during deployment. So this robot, for instance, that hasn't been to anywhere to the upper right-hand corner is still able to recover the room geometry in that area. And this essentially means that they all have a shared representation of the space, even though they haven't all traversed it, which is really nice. Compared to baselines, actually, this is where we start to see the benefit of using Dino. Baseline methods can't solve this problem. They're using some, specifically some mechanisms for consensus that blow out the gradients on the neural network. And so they converge essentially to degenerate solutions for the problem and aren't able to escape those minima. It shows that our method is essentially more sensitive to these kinds of neural network optimization problems. Finally, to kind of highlight the broad applicability of our algorithm, I'm going to briefly touch on a multi-agent reinforcement learning problem that we worked on. And so in this work, we have some pursuers in red and an evader in green. And this evader in particular is faster than the pursuers, so it has a higher sort of base velocity. And so in order to catch the evader, these pursuers need to collaborate together to sort of corner it in one area so that they can catch it. And so what we're showing here is kind of a different regime than the typical multi-agent reinforcement learning work, which is that not only is the policy distributed, meaning that each robot has its own, each pursuer has its own neural network policy, but also the optimization is distributed. So even though this is a highly non-stationary problem, we're able to use Dino to solve for pretty good policies that not only perform well, but each robot converges to a policy that agrees with all the others. So you can use that to say, do things like predict the actions of another robot if you wanted to. Great. So that has been distributed neural network optimization. I'm going to do a little time check here. Okay, great. The last work is my most recent work, and this is super hot off the press, like last week hot off the press. So I'm going to try to do it justice. It's a little bit rough around the edges, but I hope it's good, and I hope the idea comes across. So this is collaborative Gaussian splatting. What we're interested in doing in this work is to build maps that are shared by robots. And what I mean by that is there's this idea that in the future, we're going to have many, many different kinds of robots out in the world. And by having all of those different robots out in the world, we sort of have this opportunity to have some collaboration between them. But before any robots can collaborate, they need to have a shared spatial representation. And what that means is if two robots enter the room, but they don't agree on the shape of the room or where they are in the room, they can never hope to collaborate. And so what we're interested in doing is creating super high fidelity maps of both indoor and outdoor spaces using as wide variety as possible of robots. So here I'm showing a ground robot, maybe a quad rotor, and a delivery drone all working together to sort of map the outside of this building, but they could also just as well enter the building and also map its inside. We're going to shift away from distributed networks to centralized networks so that we can take advantage of some existing Wi-Fi infrastructure in these areas. And the type of map that we're going to create is going to be a Gaussian splat. And now we're using Gaussian splatting, which is a relatively new scene representation from the computer graphics community, to do the mapping because it is able to create highly, highly detailed maps, and they're really well suited for robotics applications. And I'll talk a little bit more about that later. So what is Gaussian splatting and how does it work? Because it doesn't really sound even like a map. I don't know what it sounds like. It's kind of a weird name. But it's actually really, really interesting and uses some techniques that are really, really innovative, I think. So to start, let's start with a really, really basic example. So imagine instead of the whole world that we have out there, the world is just some ellipse floating in the middle of nowhere. And we're able to put some cameras in this world, and these will eventually be our robots, but for now they're just cameras floating on space. And those cameras make observations of this ellipse, right? They capture images. So you can see here sort of the perspective of this camera is just an ellipse in the center of its image. And what we can do if we want to create a map of the world, in this case, this one ellipse, is take a guess at where that ellipse is. So you can see our guess maybe doesn't perfectly align, but it's pretty good. And it's, you know, almost the same color as this purple ellipse, but maybe not perfect. And what we can do is, and this is really the core innovation of Gaussian splatting, is perform what's called differentiable rendering. So we take this ellipse and we project it onto our cameras, and then we say, okay, now we have these images of what we think the map is, and we know that the true world looks like this in our images. So we can compare those two images, i.e. take what's called a photometric loss. And by doing and computing that photometric loss, we now know where our model is wrong and where it's correct. So because this process of rendering was differentiable, we can actually directly take that loss, pass it, propagate gradients all the way through this differentiable rendering function, and update the value of our guess of the world, right? So now we have a slightly more closer matching ellipse that has approximately the correct color of the true ellipse that we have in the world. And, you know, this doesn't just work for one ellipse. If we have other shapes, we can use multiple ellipses to approximate that shape here. And I've been saying ellipses a lot. I forgot to mention Gaussian splatting, the derivation of the name, comes from the 99% confidence interval of 3D Gaussian. So a lot of times this gets conflated together in the literature, but essentially they're the same thing. These are just some geometric primitives that have ellipsoidal shapes. Great. So it's a bit of a stretch, but now but if you take, instead of just simple models like this and simple images, if you take pictures of the real world and apply this technique of differentiable rendering and computing this loss and optimization over many, many ellipses, not 3 here in this case, but say hundreds of thousands or even millions, then you can create super high fidelity maps of the real world. So in this case, you can see here some statues, in this case, Rodin statues, in the front courtyard of Stanford here. And this map isn't like a super curated data set. Tim Chen, who actually created these visualizations for me, so thank you, Tim, just went out with his phone, I think, and recorded a video of walking around these statues. And actually, you can see that we get not only accurate geometry, but accurate lighting conditions within the scene. So this back arches over here are lit up more by the sun than other places, and shadow effects, different lighting effects, but also the underlying geometry. So if we show the ellipses without any color, is also highly accurate. So we can use this for things like contact modeling and those sorts of things. What's really cool and kind of the inspiration for why I wanted to use Gaussian splatting, particularly for this problem of mapping with many different devices, is that you can use all kinds of different camera models to create these Gaussian splats, and you can use them at the same time in the same map. So a ground robot with one kind of camera and another robot with another could both contribute to the same map, and it works just as well because of that differentiable rendering process, which is very flexible. And then, so the two things we need are poses for the cameras that took the images themselves, and then sometimes some geometric information about the scene to initialize the positions of these Gaussians. And even though we do require it, or we don't necessarily require it, we could randomly initialize the Gaussians, it really helps to get sort of accurate and clean geometry in the final product. So I mentioned that these Gaussian splatting maps are really useful for robotics tasks, but I really would like to highlight that by presenting briefly some work that we did in the MSL. In two of these projects, this one up here and this one down here, I actually worked on or participated in. But the things that I want to highlight about Gaussian splatting that are really amazing for robotics. First, detailed scene reconstruction. So I'm not going to talk about what this is yet, but you can see on the left-hand side, this is actually a rendering of the Gaussian splatting scene. And you can see here, with a camera just mounted on a drone flying around in real time, we can reconstruct this HDMI cable wire that's sitting on this desk in high fidelity and almost full geometry. And this is basically impossible with any other mapping framework that exists for robotics right now. So it's super accurate. So in this particular example, we build a Gaussian splatting map in real time with the data stream from the drone. And then we use that Gaussian splatting map to synthesize a reactive controller that works with a teleoperator to avoid crashing the drone. So you can see on the right-hand side here, the person who's teleoperating this drone is actually just driving the drone forward and trying to crash it into the side of the desk. But using our reactive controller, it actually gets pushed up and over the desk instead. Down here, you can see some work also from Tim of using Gaussian splatting maps to plan safe trajectories, in this case through the same scene as we were looking before. And because the super accurate geometry of Gaussian splats, as well as the fact that because we're using very simple geometric primitives, inference is very, very fast. We can compute these trajectories in real time and actually use them to directly fly robots, which if you check out this work, we have some good videos, I think, for that. And then finally, one thing that I haven't really touched on yet in Gaussian splatting is the fact that you can embed all kinds of other information in them, not just color information. So in this example here, we embed semantics, in this case, clip semantics, into the scene. And on top of the semantics are also embedded affordances. So this is where in an image a robot arm should pick something up. And so this is excellent, excellent work from John Tucker and Ola Sharinwa in our lab that shows that all you need is a highly accurate map. You don't need to do a bunch of reinforcement learning or behavior cloning to do grasping. So I think this is really cool and runs kind of counterculture to the typical grasping methodologies that a lot of people employ these days. Great. So this, I think, hopefully serves to convince you all that Gaussian splatting is super cool for robotics and super useful. One last thing I would like to touch on, and Mac actually mentioned it a little bit in his introduction of me, is that there is a step that we need to take to actually be able to build Gaussian splatting maps for in robotic situations. So I mentioned that this scene representation originally comes from the computer graphics community. And in order to pose all of the cameras, the typical workflow before was to take a video of the scene you're interested in mapping, download it onto your computer, run some very costly and very slow structure from motion algorithms to extract the actual positions of the camera frames, and then train the Gaussian splat. So this whole process takes like 3 hours at minimum, especially running the Cole map step or the structure for motion step is especially slow. So all we did basically is observe that, hey, in robotics, we basically solved pose estimation, I don't know. It's still hard, but we can do it. And so instead of doing this cumbersome structure from motion step, all you need is an active camera feed from a robot and its current localization estimate, so its current SLAM estimate. And then using those two things, you can then directly train a Gaussian splat. So down here, you can see a robot is actively driving through this scene and at the same time sending its images back to a mapping server and training this Gaussian splat at the same time. So this is online Gaussian splat training. And now we're not the first people to propose this kind of pipeline, but we do have probably one of the maybe 2 or 3 only open source existing implementations of this. And specifically ours is designed to work with a wide variety.
called absolute orientation, which essentially links the coordinate frames of the unaligned robot and the aligned robot, and then use that to update the relative transform and put all of the robots in one unified coordinate frame. It's a little bit complicated. Just take my word for it that it works. It's not the fun part of this, but it did take me forever to figure out. So how do we actually do multi-robot Gaussian splatting? Initially, I was like, oh, it doesn't really matter. You know, we're just going to take all the camera feeds and just plug them into the Gaussian splat. It'll figure it out. Turns out it's a little bit harder than that, as things usually go. So the first step is we really need to make sure that we're processing the different kinds of depth information that we're receiving from the robots in a consistent way. And so we do this using a pretty simple trick, which is just always taking whatever depth information we receive, back projecting it onto the camera frame that's associated with it, and setting the size of the Gaussians that we initialize to 1 pixel wide. This tends to work really well, although it starts our maps a little bit more conservatively than other initialization approaches. The second step, and this one was really a pain to figure out, was how to get appearances to match between different robots. So anyone who's taken a picture with a cell phone knows that one cell phone might take a picture of the same scene, and another, like say an iPhone 6 or something, might take a picture also of that same scene, and they might have vastly different colors. So you can see here, this is a sample image from the Aria headset and one from the Turtlebot. And they have vastly different lighting conditions, even though they're looking at exactly the same thing. So what we do is we add some extra compensation factors in the form of linear bilateral grids. It's a bit of a mouthful. And we use them essentially to correct the lighting in the scene. So now when we render in our map, the lighting is consistent between two robots, even though the source images that we use for training are pretty vastly different. When we embed semantics in our scene, we do so not by augmenting the channels in Gaussians, which is kind of the common approach, I would say. Instead, what we do is we learn an auxiliary continuous semantic field underneath our Gaussian splatting framework. And then when we want to know the semantics of a Gaussian, we just query its mean or where its location is in that field, and that's the semantics. And so we do this with an additional loss on top of all of the other Gaussian splatting things. And then finally, it's pretty common to also optimize the poses of your cameras. So we have some inputs from SLAM, but we need to fine tune them to get the best results out of the map. So this is a common step to do, but actually we add a pose refinement step where we optimize also the alignment that we got from our inter-robot alignment module. And so this helps our world frame be more consistent between all the robots based on the information from the map. And then finally, this is all wrapped up in an online training framework that is basically a modified version of what I've talked about before. Okay, so what does that actually look like in practice? Here you can see a bird's eye view. This is actually a mesh extracted from the Gaussian splat, not the actual Gaussian splat. And you can see here the different robot trajectories, or at least hopefully they're a little bit small on the screen, sort of as they enter the map, and then you can see the map refine itself as all of the robots are aligned. And they're all contributing their data. On the right-hand side, you can see highlighted where in the map each robot contributed data. So this green robot was only in this far right room, and this blue robot was only in this hallway here. Practically speaking, what does it actually look like? Do you want to play that video, Jen? Thanks. This is actually trained in the room you're all sitting in today, so hopefully you can have some reference. But you can see that the Gaussian splat that we recover from using our method, Hammer, is actually fairly accurate. In regions where we have bad supervision, there are some sort of rogue Gaussians, but in general, you can see that we reconstruct very accurately the details of the scene, including all of this hallway over here, flying down the hallway here. We can see the bulletin board. You can actually almost read the text that's on the papers, not quite. Maybe if I spent a little bit more time optimizing this, we could. And then looking into the MSL here, you can see that we recover all the desks and the different geometry of this chair and all of those sorts of things. Great. So this is all built collaboratively using 4 different robots using our method. And then finally, to prove kind of that our map is not only buildable, but also useful, I'd like to highlight a quick language-driven trajectory optimization sort of demo that I cooked up, which is basically taking the last known position of all of the robots in our map and planning trajectories from those last known positions to a bunch of semantic goals. So in this case, we're querying our map for semantic goals like vending machines, so the vending machine outside, conference room, also espresso machine, maybe couch. And so you can see those end up with a bunch of different locations in our map because we take those semantics of the Gaussians, find the place with the highest relevance, and then map to it, or plan to it. And so that's the 4 different robots planning. So I hope that convinces you that not only can we build these maps using our method, but we can also plan to semantic locations in them. And that is the end of my talk. I think I'm running short on time, or over on time, so I'm going to move quickly. I'm going to jump right into some acknowledgments, because this PhD would not have been possible without a number of people, and so I would like to say thank you to them. Firstly, I would like to thank my committee for sharing this time with me today. I know it's hard to get everyone in the room, but you've all made it very, very easy, so I really appreciate that. I'd like to thank Mac especially. This is a picture of me preemptively getting graduated a couple of months ago, so hopefully things today go well. There's a lot I want to say about Mac, but I really want to highlight the fact that when I came to Stanford, I already knew that I wanted to work with Mac. I didn't really know him at all, but I loved his work. I was really interested in the work that the MSL was doing at large, and so I thought it would be a great fit. And what I came away with was I got super lucky. Mac is an excellent advisor. He is an excellent mentor. His enthusiasm for the work that we do in the MSL is incredible. I think he's probably the only person in the world that's more excited about my work than I am. So that is just like an immensely wonderful thing to have in a mentor, and I deeply, deeply appreciate the 6 or so years that we've been working together. I'd like to thank everyone in MSL, all of my collaborators, all of the people that I've had the pleasure of working with over the last few years. Without all of you, none of the work in this PhD would have been done, because I do my best work when I'm working with other people, hence the collaboration theme in my PhD. And so it really has been a special time for me, and I'm super grateful to have worked with all of you smart people. I'd like to thank all my friends, many of whom are in the room today, and some who are not. I think probably my PhD would have been done a little bit faster with all of you around, but it certainly would have been much less fun. And so I deeply appreciate all of you being around. Many of these people have helped also inform my research. They're all super smart, and I very much appreciate them. I'd like to thank my family. Nobody could make it today, mostly because they all live far away, but I know they're on Zoom, and so I really appreciate their support. They may not all know about exactly what I'm working on, but they certainly all are very supportive, and so I really appreciate all of them. I hope to have a little bit more time to see all of them soon. So I'd like to thank, especially a special thanks to my partner Adrian, who's here today. She worked a 15-hour shift in the hospital last night, and she still got up to come see my defense. She has been incredibly supportive during this PhD. Everything I could have asked for in a partner. When I started this PhD, we had to do 4 years of long distance while she was in med school in Chicago and I was in Stanford, and we made it through that. We made it through me being not able to talk about any date past November the 19th for basically the last 6 months. So I think based on the experience of this PhD, we're gonna make it through the rest of anything else that can be happening. So I really appreciate her and all of her support. Finally, I'd like to dedicate this work to my mom, Dr. Isabel Arredondo. She unfortunately passed away during the course of this PhD, and so she can't be here today. But she was undoubtedly the reason that I am in research today. She herself was an academic and loved to work, loved her work, and was super excited about her research. I don't think I would be the person I am today without her, and so I'd like to dedicate this to her. And I know if she were with us today, she would be in the front row. So, yeah. And that has been my defense. Thank you all for being here.
for a few questions, and then we'll ask everybody except for the committee to leave, and we'll do the closed door session. Questions? Yeah.
Hi, this is, oh my god, incredible, by the way. It's really, really cool. I was just wondering, when you were explaining the Dino X method that you developed, I was wondering if you had kind of about federated learning at all, because it seemed a bit similar.
Yeah, I actually last minute this morning took out some stuff on my related work on federated learning just because it was becoming maybe a little bit slow through that section. Federated learning is also a distributed method for doing neural network optimization, but it makes some assumptions about the kinds of communication that you can use. And so it relies on a central kind of hub and spoke model to do the optimization. So you need some leader nodes. So the main difference between our work and theirs is that we don't require those kinds of explicit hub and spoke graph structures in our robot communication. But yes, it's a very actually similar idea. And typically it requires higher bandwidth as well than the kinds of things we're doing. Great.
So in the collaborative Gaussian splatting work, do you have to deal with the fact that potentially the robots can look at each other, and then like the robot which is moving might violate the safe assumption the scene is stationary?
Yeah. So we do make stationary scene assumptions. I don't explicitly deal with it in my data recordings. Actually, Gaussian splatting, like while it does make a stationary scene assumption, if there is like maybe one object that moves around a little bit, you can deal with it and it kind of gets blurred out in the scene. In particular, if you had two robots that were like right next to each other for a long time, it would mess up your map. And so it's not something I do, but something I've thought about is doing some basic kinds of segmentation to remove dynamic objects from the scene, at least until we can do dynamic object modeling, which is obviously a goal later for these kinds of mapping frameworks.
Cool. Maybe one more question, if there is one. No?
What was
Sure.
it that led you to
Let's give
Gaussian
Javier a
splat?
hand.
Oh, sorry.
I'll ask you all to leave the room, please.
Bravo.